Good morning, ladies and gentlemen. Please raise your hand if you did not get red mark for today. The second. Great. Let's go ahead and get going. So we need to be able to apply our derivative shortcut rules, whether that is our new inverse trig functions or our old trig functions, right? Or any combination thereof. So we've tried to mix up some of our new rules, and that's the subject of our Moodle post this week. You guys did such a great job on your antiderivatives, or Are You My Mommy derivative post last week, that we went ahead and decided to do antiderivatives round 2, and this is perfect timing for your rules quiz coming up. So once again, this week's Moodle discussion post is similar to last week's. I do ask that if you used a product rule last week, then use a quotient rule this week, right? I've also asked that you work on our other 4 trig functions, right? Like our secant, cosecant, tangent, cotangent. If you incorporate those in your rules, that'll help practice the new ones, as well as the inverse trig, right? The inverse trig rules. And so we've got our inverse sine, inverse cosine, inverse tangent, inverse cotangent, etc. If you work some of those into your antiderivative rules, that would be great to help practice. Again, our Moodle post this week then is antiderivatives round 2. All right, let's go ahead and get going. So we can apply our shortcut rules now to inverse tangent functions. If y is given by the inverse tangent of e to the x, then we know y prime would be 1 over 1 plus the input squared times the derivative of the input. How do we know that? Because we memorized our shortcut words, our rules sheet, right? We memorized those words. So the derivative of inverse tangent is 1 over 1 plus the input squared times the derivative of the input. And we know our input in this case wasn't plain old x, it was e to the x. So the derivative of that input is also e to the x. You can rewrite that then in simplified form. We'd write e to the x over 1 plus e to the 2x. So raise your hand if you already had this. So who had the derivative of inverse tangent correct? Way to go, you guys. That's perfect. Let's just switch this over there a little bit. There we go. PDFable, Jake, PDFable, that's what we're striving for. Take a look at number 2. Number 2 is another inverse trig, an inverse trig function. We know our derivative for inverse sine is 1 over the square root of 1 minus input squared, closed radical, and then times the derivative of the input on top. So in application of the rule, we would get 1 over square root of 1 minus input squared, and then times the derivative of the input. It's just that my input wasn't x, it was x over 3. So times the derivative of the input is going to be times 1/3. Well, we can make that look a little bit nicer. We would say then our final answer would be 1 over 3 root 1 minus, and I'd probably write that as x squared over 9. You could certainly leave it as quantity squared, but I'd probably write that as x squared over 9. Go ahead and take a look at number 2 in red and raise your hand if you had that already. Did you have that already? Inverse sine? Hey, great. Good news. And number 3, if p is given by the natural log of square root of x, then p prime is given by a couple ways to do this. So we could use our natural log words, which incorporate the chain rule from our rule sheet because we memorized it. The derivative of the natural log of a function is 1 over the function. So that would be 1 over square root of x, and then times the derivative of the function. Recall that square root of x is actually a power function. It's x to the 1/2. So to differentiate it, we do exponent times the base raised to the 1 less. What's 1 less than 1/2? Negative 1/2. And so this ends up, there we go. So this ends up being a radical, right? A radical on the bottom, and I already have 1 over radical. And so how are we going to write that? Well, we could rewrite this as 1 over square root of x. There's my first one. Times, and here's my second one. This would be 1 over 2 root x again. So it appears as though I'm getting a simplified derivative of 1 over 2x. Not to be confused with 1/2 x, right? This is the x on the bottom, so a hyperbola there. So raise your hand if you get number 3. Did you get all the way to the end of number 3? Yes! You guys are doing great. Okay. How could we have done number 3 differently and saved a little bit of this exponent simplification? Again, that's recognizing your properties of logarithms and rewriting my original function p first, and then differentiating with an easier rule. What? Well, if we were to recognize that this x, right, this square root of x inside is equivalent to x to the 1/2, and then used our properties of logs, and in fact the log of a power property, which allows us to bring down that exponent as a constant multiplier in front, I could have been left with a simpler differentiation rule. You don't have to do that, but notice that this rule does not involve a chain rule. This would just simply be a constant times the derivative of ln x. So your final answer would be 1/2 times 1 over x. The derivative natural log of x is 1 over x. What's 1/2 times 1 over x? 1 over 2x. And so you certainly could do this. You could do this either way. Of course, then you have to remember your properties, right? But either way, we should generate 1 over 2x. Awesome. Questions on your shortcut rules? Great. Let's go ahead and take a look at our tangent line then. Algebraically, find an equation of the tangent to f equals cosine of x at x equals pi over 3. And so we need three things in order to write the equation of the tangent line. We need the x coordinate of the point of tangency, the y coordinate of the point of tangency, and the slope of the tangent line. This is like x equals a, right? We need the y coordinate of the point of tangency, so that's my original function f of a, and we need the slope of the tangent line. Where would I go to find the slope of my original function? Right? Where would I go to find the slope of my original function? Sophia? The derivative equation. So we'll go ahead and algebraically calculate the derivative equation using my shortcut rules. If f is given by cosine of x, then what's f prime? Meg?
Opposite sine of x.
Opposite sine of x. Thank you. So that gives me a derivative equation, which can be used to evaluate the slope of my original curve anywhere along it. Where do I want to know the slope of the curve? Jake?
At pi over x equals pi over.
Absolutely. So the slope of my tangent in green is given by the value of the derivative function f prime evaluated at my x value concerned, pi over 3. Therefore, my slope of the tangent line m must be opposite of sine of pi over 3. Good thing we have our unit circle memorized, right? We know that the sine of pi over 3 is right here, root 3 over 2, and the opposite of that would be negative root 3 over 2. So it appears as though the slope of my tangent line is opposite of root 3 over 2. Raise your hand if you had this for your slope of the tangent line. Slope of the tangent line? Great. Now all we need to do is generate our equation of the line tangent to the curve. So we've got our x coordinate of the point of tangency for free. We've got our y coordinate of the point of tangency. Well, not yet. We still need to get our f of pi over 3 in order to generate the y coordinate of the point of tangency. That would be given by cosine of pi over 3. And that equals, the cosine of pi over 3 is 1/2, so I'm getting 1/2. And now we can finally generate the equation of the line tangent. Do I have space for that? Not yet. So we'll go ahead and do my age-old point slope form. Y minus y sub 1 equals m times quantity x minus x sub 1, where x sub 1 comma y sub 1 is the point of tangency, and m is my slope of the tangent line. And so all we need to do is plug our values in that we found. So we've got our pi over 3, we've got our 1/2, I'm sorry, 1/2. We've got our slope of the tangent line, which was negative root 3 over 2. And so we'll have our equation now. It'll be y minus 1/2 equals my slope, right? My slope, negative root 3 over 2, times quantity x minus pi over 3. If we're simply asked to generate the equation, we could leave it here in point slope and stop. However, if we want to check graphically, it makes sense to solve this for y because I have to enter in my y equals many. And so I would just do a one-stepper and not mess around with distributing this through the parentheses and worrying about pi's and radicals, I would probably just add over the 1/2 and enter this as is, so I don't have to worry about messing up with positives or negatives, right, or approximations or pi's. I would leave this as negative root 3 over 2 times quantity x minus pi over 3 plus 1/2. And I would check a graphic. So let's go ahead and see. On my emulator, we'll go ahead and enter our original equation, y equals cosine of x and we could, let me zoom trig and see if that gives us an okay spot. So we'll zoom trig is 7. Got you. So that must be giving our 4 pi. And let's go ahead and enter our calculated y tangent line, y equals tangent line. So that was negative root 3 over 2. Ooh, we don't want that. So negative root 3 over 2. How's that? Is that better? Times quantity x minus pi over 3. Close. Plus 1/2. Let's see how that goes. So we've got our slope of the tangent line. We've got our x coordinate of the point of tangency, our y coordinate of the point of tangency. We'll go ahead and see how this goes. Here comes our tangent line, and how can I check? I can't really tell. Does that look like it's touching at x equals pi over 3? Well, I could just visually inspect by entering trace pi over 3, x value of concern, and see if the cursor jumps on where it looks to be tangent, and it does. Secondly, I could ask the calculator to draw a tangent line and do it numerically and compare with my algebraic. So numerically, right, my calculator can generate an equation of tangent line. What commands do I press for that? Who remembers what commands I press for that? You don't remember what's commands? So, Savannah?
Second draw 5.
Yeah, second program is draw, right? 5 is tangent. Enter x value of concern. I want to do it at pi over 3. So I'll tell the calculator, second pi over 3, x value of concern. Enter. And voila! It just overwrote that red line style that I had for my own y equals menu with the blue calculator numerical development. And it looks like if we kept those decimals and put in the original, we see that we match exactly. So that's pretty sweet. We're gonna make these a little bit bigger. Yeah. Maybe we can stack them. Maybe we could play Tetris on the smartboard. That would be pretty sweet. Okay. Raise your hand if you have the tangent line right. So who had the tangent line correct? Yes? Yes? Good job. Excellent. Way to go. What questions do you guys have about then today's Bellwork? All right. So let's go ahead and take a look at our OTL number 4. Good morning, man. If you'd make sure that your heading is on top, please. Name 2A, number 4. And let's go ahead and give yourself credit for those who completed out of 31. In pencil, divide, enter, multiply by 2. If you kindly staple your half sheet along with your bookwork because of the graphs on back. I appreciate that, and keep the stapler going around. Thank you for giving yourself credit for those that you complete out of 31. Divide, enter, multiply by 2, and then box it in front of canvas score nice and big on top, please. Round to the nearest half point, 0 to 2.
Good morning.
No,
I know. That was jammed over there.
Alright, you got it, or you want me to?
Oh, sorry. It's because you've been using different colors in the whiteboard.
We just got open up a new marker. Thanks for noticing. I was excited. Made my Friday. All right, thanks. Go ahead and pass this in from back to the front rows. Please make sure they're facing the same direction. I know we're a little out of order for our quizzing formation for advanced algebra next hour. But thanks for your help anyhow. Thank you. Thank you. Thank you. Everybody go with number 4? Number 4? Okay. Ladies and gentlemen, today we're going to develop the connection between differentiability and continuity. And so we spent a fair amount of time in Unit 2 developing the notion of continuity for the calculus definition, right? In order for a function to be continuous, we need the left-hand limit to match the right-hand limit, and then that guarantees that we're nice and smooth. We have to fill in that hole by defining the function, right, at x equals c to equal the value of the overall limit. So, for a given function, if the limit as x approaches c of f of x exists and equals the value of my function at x equals c, right? For all x equals c, the function then is continuous, right? It's all continuous. And so this is my continuity. Today, though, we're going to look at differentiability. We'll see how this now definition connects with differentiability. Together in groups, you're going to work on your 2-6 activity, differentiability and continuity. I need to check your yes-no responses at the end of 1D. So that'll be the first stamped eligible exercise. Then you're going to look at those results and come up with a conclusion for 2B. That'll be your second stamped eligible item. And then you'll continue working with your group through 3E. We're going to come back together for number 4. So once again, it's a fairly short activity today. We're going to come back together for number 4 and apply it. And then after our closure, you should get a little chunk of time to work on your OTL. So kind of a light day today. Remember, your rules quiz is coming up next class period. I'm going to go ahead and pause the recording at this time. And then I ask that you scoot together in your small groups of 3 or 4. Okay, ladies and gentlemen, thanks for your help returning your desks to the regular positions. By now, everyone should have your 3E stamp, and then we're going to go ahead and take a look at number 4. So last page of your 2-6 differentiability and continuity handout. Let's come together and take a look at the graph of f, which is a piecewise defined function. Everyone will need your graphers. And recall, bless you, that we can enter a piecewise defined function in our graphing calculator by using those Boolean operators. That second math is the test menu, and you have the logic symbols there. So everybody, let's go ahead and remind ourselves how to do that. I'll go ahead and use my emulator. Let's use the same window, you guys. So let's go -1 to 5 for x's, and let's go -1 to 8 for y's. That way we'll all be looking at the same picture. So once again, -1 to 5 and -1. Oops. So recall, we can enter our function definition and then divide any term by, right, quantity and then domain restriction. And since there's only one term in that top piece of my function, f of x given by x squared, I'll divide that term by, and then I'll do my Boolean operators. I'll do second math is the test, and we want the less than 2. So I need to put the variable button first and then less than 2. And I've already gone to my less than 5, so I need to go back and insert my parentheses and x. There we go. So I need parentheses, x less than 2. Close parentheses. So I divide by the quantity and then my domain restriction. For my y sub 2, that will be my second piece. I'll go ahead and enter opposite of quantity, x minus 3 quantity squared. fine, plus 5. And then I'll divide that last term by, again, quantity domain restriction. My quantity now is x greater than or equal to. So second math is my test, and I want the fourth option for greater than or equal to 2, close. So I'm going to go ahead and cover that up a little bit so that we can have enough space for our screenshot for our picture. Let's go ahead and see how we did with our piecewise function definition. So there's our left piece, y equals x squared, and there's our right piece in red. That is also, right, that's also a parabola. It's just now it's an upside down parabola because of that negative multiplier in front. Raise your hand if you have this picture. So we got this picture. Great. Does our function appear to be continuous at x equals 2? So does our function appear to be continuous at x equals 2 as we look at it? Well, keep in mind that my pixels on my calculator, right? I'm held back by the capabilities of my calculator, and it takes a finite number of points, evaluates them for a given function rule, plots them, and then connects them. And so here we've got our changeover in definitions. However, does it appear like the left-hand value of the function would be matching, right? Matching the right-hand value of the function if I continue to zoom in at x equals 2? Visually, I would say yes. So visually, I would say yeah, it appears to be continuous. My picture, right, there's definitely a hole there, but that's because of my changeover in definition. Now let's go ahead and use the definition of continuity to determine if the function is truly continuous. And so clearly through function inspection, it's not enough just to say it looks like it. In fact, when we first look at our graph, there's a hole there, so it looks like it's not continuous, right? It looks like a removable discontinuity. Let's see if it is in fact continuous using the definition of continuity. So for us, we know that our function is continuous at x equals c if the limit of f of x as x approaches c is equal to the value of the function at x equals c. In terms of notation, that is, the limit as x approaches c of f of x needs to exist, and it has to equal the value of my function at x equals c, namely f of c. As we go ahead and take a look at our definition of f above, what is my c value, right? My x value concerned in this case. Preston? 2, and so we're investigating right around x equals 2. So what do we need? Well, we need our value of my function, f of 2. So f of 2, let's see what that is. We'll go to my original definition. And which piece will I use to evaluate the function when x equals 2 based on my piecewise defined definition? So which piece? Annika?
The second one.
How come?
Because that's where x is equaling to.
Absolutely. There's our or equal to, so we'll plug in 2 into my second definition to work it out. 2 minus 3 is negative 1. Squared is positive 1 times negative is negative 1 plus 5 is 4. I'm getting 4. I'm getting 4. So I'm getting 4 for the value of the function. Now let's go ahead and compare that with the value of the limit. In order to have an overall limit exist, what has to be true, Marissa?
F of C value we just found stays the
Right. Yes. For the value of the limit to exist. Forget about the f equals c. What has to be true for an overall limit to exist?
Both sides have to be equal.
Absolutely. So let's go ahead and take a look at the left-hand side, the left-hand limit, and the right-hand limit. Thank you. All right, which piece will we use in my function definition for the left-hand limit? Paul?
The first one.
The first one, good. So the left-hand limit would be the limit as x approaches 2 from the left-hand side of x squared is my x value concerned 2 in the domain of my expression, x squared? Certainly, so I can evaluate through direct substitution. The limit as x approaches 2 from the left-hand side of x squared equals 2 squared is 4. So I'm getting 4. Which definition will we use for the right-hand limit, Savannah? The bottom one, good, thank you. So the limit as x approaches 2 from the right-hand side is given by negative opposite of, x minus 3 quantity squared plus 5 is 2 in the domain of this expression? Yes, in fact, we just evaluate that expression once to get the value of f at x equals 2, and I get 4. Does the overall limit exist? Yes. Marissa stated the left-hand side limit had to match the right-hand side limit, and they do. Therefore, the overall limit exists. And is it equal to the value of my function at x equals c? Yes. Is the function continuous? Yes. So we've got, so the overall limit as x approaches 2 of f of x exists, it equals 4, and this in turn equals f of 2, which equals 4, so we're good to go. That is the coolest looking T I've seen in a long time. I was like, check, check. Therefore, f is continuous at x equals 2. But that's old news. We've already looked at continuity in great detail, right, in Unit 2. Now we're interested in differentiability. And so does the graph appear to be differentiable at x equals 2? Well, let's take a look at our picture. Does it appear as though the graph is differentiable at x equals 2? Go ahead and turn to a person near you and say whether it appears to be differentiable. Does it appear to be differentiable? Yes, I long for our partner pairs as well. Darn advanced algebra testers. So nice. All right, this is an opinion, right? Until we do it mathematically. So this is an opinion. So does this appear to be differentiable by looking at the graph? So what did you guys come up when you were looking with it, right? What did you guys think? Anna and Evie?
No, we said no.
You said no? Raise your hand if you said no. Thought no? Who said yes? Everybody say yes? Yes? Okay, so we're going to decide then whether it is or isn't, and we can do that mathematically because we have a function definition. So does it appear to be differentiable? I'm going to put a maybe, because I got no's and yeses. Maybe. And how could we do a face? Maybe like a... Let's use our proven shortcuts to determine if the function is truly differentiable. In order to be differentiable, we must have continuity, because otherwise we wouldn't have a place to attach the tangent line. We don't know where to attach the tangent line if we don't have continuity. Do we have continuity? In great detail, we've proven the continuity. So now we just need what to be true to be differentiable at x equals c. Left-hand slope has to match the right-hand slope. If the left-hand slope matches the right-hand slope, then my function's overall derivative exists at x equals c. So let's do it. Left-hand slope would be the derivative from the left-hand side. How would I write that with notation? The limit as x approached 2 from the left-hand side of now not f of x, but f prime of x. We need to consider the left-hand slope. So notice how we're now doing f prime for my expression, right? Not just regular f. Which rule will we use to develop the left-hand slope? We'll use the top definition, again for the same reason, because x approaches 2 from the left would follow the top definition. And we get the limit as x approaches 2 from the left of, what's the derivative of x squared? 2x. We can evaluate that using our shortcut rule. Is 2 in the domain of f prime? 2x? Yes, so we can evaluate this limit through direct substitution, and we get 4 for my left-hand slope. So our left-hand slope, we got 4. Let's consider the right-hand slope. The right-hand slope can be gained exactly and algebraically by differentiating my bottom definition. And so again, we'll start with our general notation. The limit as x approaches 2 from the right-hand side of f prime of x, the derivative of my original f. And to get that, we'll go ahead and use our shortcut rules, but we'll apply those shortcut rules to my second function piece. What? Can I differentiate that with a shortcut rule? What shortcut rule would we use to generate f prime of x using the second definition? What is my overall category of functions here? What rule are we going to be using? Damon? Power. This is just a power rule. It can be a power rule with constant multiplier, power function, constant. So I'll simply use my words that I memorized for my rule sheet. The derivative of a power function is exponent times the base raised to 1 less times the derivative of the base. Make sure we keep our constant multiplier in front. Exponent 2 times the base, x minus 3 raised to 1 less, the first power, times the derivative of the base. What's the derivative of quantity x minus 3? Still just 1, and then plus the derivative of 5 is 0. And so I simply get negative 2 times quantity x minus 3. I want to make sure that we can read this as x minus 3 though. Very nice. Is good. Is 2 in the domain of this expression f prime? Yes, it is. So we can evaluate through direct substitution. Let's do that. Ready? Go. 2 minus 1. No, 2 minus 3 is negative 1. Times negative 2 is positive 2. Does my left-hand slope value match my right-hand slope value? No, and so while the function was continuous at x equals 2, it clearly is not differentiable because the left-hand derivative value does not match the right-hand derivative value. Can we do a sideways thing like that, or does that just look like h? Doesn't equal? Not the same? Okay.
It's close enough.
it's sideways. If you turn your head sideways, then it's a not equal. Does not equal. 2 does not equal 4. No way, Jose. Or you could think of those as train tracks, and the train tracks have been broken. Right? See that? Does not lead to. Don't take this route. Keep out. Stay back. Can't get there from here. Nothing to see here, folks. Turn right around.
Equals slash.
All right. So what can we say for our conclusion? Is the function truly differentiable? No. F is not differentiable because the left-hand slope does not match the right-hand slope. And I'll go ahead and use calculus notation. The limit of f prime of x as x approaches 2 from the left does not equal the limit of f prime of x as x approaches 2 from the right. Awesome. What questions do you have about E? Okay, then let's further connect continuity and differentiability. Suppose that f, right, is given by a piecewise defined function. In this case, we're not given values of constants a and b, and we're asked to find values of a and b, which will make the function differentiable at x equals 6. And so here we've got a new function. We need our function to be differentiable at x equals 6, and so the first piece, in order to be differentiable, would be like that second picture in 1b. You have to have continuity in order to have differentiability, otherwise we wouldn't have a place to attach our tangent line. We don't know where to attach our tangent line. So first thing, we need f to be continuous. So let's go ahead and do the continuity component first. For continuity, we need the limit of f of x as x approaches 6 to equal f of 6. So let's go ahead and find f of 6. Which definition will we use to find f of 6, Jake? The bottom one. So we need f of 6 would be evaluate, right? Evaluate my function when x equals 6, and I get 6a plus b. You guys have 6a plus b? And I need that to equal the overall limit of f of x as x approaches 6. So what do I need for that? I need the left-hand limit to match the right-hand limit for that to exist. So let's do the limit as x approaches 6 from the left of f of x equals, the limit as x approaches 6 from the left, and which definition will we use for that? Evie?
X squared.
Good, thank you. And is my x value concerned in the domain of my expression? Yes, and so I can evaluate through direct substitution. I'm getting 36. You guys get 36? Awesome. Let's do the right-hand limit. The right-hand limit will be given by the limit of f of x as x approaches 6 from the right. For us, that would be the second definition. And as x approaches 6 from the right is 6 in the domain of ax plus b for constants a and b? You bet your boots it is. And what would I get? Good. So ax plus b equals 6a plus b. All right. So for continuity, we see that my overall limit, 6a plus b, must equal 36 for the overall limit to exist, and that in turn would equal 6a plus b. So we need 6a plus b to equal 36. Great. That's continuity, but continuity only ensures a place to attach the tangent line. Differentiability adds a further requirement. I need what? For a function to be differentiable at x equals c, what must be true about the slope values? Brandon?
Slope must be equal.
Which slopes?
So the left and right slopes must equal.
Absolutely, thank you. So let's go ahead and get our left-hand slope. That is the limit as x approaches 6 from the left of f prime of x. So here we go, left-hand slope. So my left-hand slope would be the limit as x approaches 6 from the left of f prime of x. Again, we use the top definition for that. So that would be the limit as x approaches 6 from the left of the derivative of x squared, that is 2x. Again, 6 is in the domain of my f prime function equation 2x. So it looks like the slope as x approaches 6 from the left-hand side is given by 12. You guys getting 12? Awesome. Let's do the right-hand slope. So my right-hand slope would be the limit of f prime of x as x approaches 6 from the right. And I'll use the second definition. Ax plus b, right, as x approaches 6 from the right, differentiates to what? That's just a linear function. Isn't that a linear function? Kind of like y equals mx plus b, which you proved on your last test was equal to the slope m. So this would be a. So the limit of a as x approaches 6 from the right, where a is some constant. What's the limit of a as x approaches anything? A. The limit of a constant is the constant. Good. And so this equals a. For the function to be differentiable, I need the left-hand slope to match the right-hand slope. So I need a to equal 12. Notice how we haven't wrecked the train tracks? That's a regular equal. A does equal 12. You can get there from here. So if a equals 12, then a equals 12. So 6 times 12 plus b equals 36. And we can now solve for b. 6 times 12 is 72 plus b equals 36. Subtract over the 72 to solve for b. I'm going to get negative 36. Are you guys getting negative 36? So let's go ahead and consider our calculated values of a and b. So we think a equals 12 and b equals negative 36. Suspect. I'm not so sure about that. Can we go ahead and informally verify that our equation is differentiable by graphing on our calculator? right? If I graph on a calculator, certainly. We could use our domain restrictions again, right? And manipulate the window here to make this a little bit nicer. Let's see where that's going to put us. And so we want A to be 12 and B to be equal to negative 36. Let's try that. So in my regular function definition, let's still do x squared. I'm going to toggle over and make this now 6. And for the second definition, I'm going to clear that out and put 12x minus 36. Is that right? I'll restrict that portion of the graph to only include those values where x is greater than or equal to 6 by doing divided by quantity x, and I want greater than or equal to 6. So second math is test. Greater than or equal to is fourth option. 6, close. All right. So let's go ahead and take a look at my graph, knowing that I'll probably have to adjust the window. We're going to go for x equals 6, so I'm not even in the picture yet. So let's go ahead and adjust our window. We need to go past 6, so let's go ahead and do maybe 2 to 10. And let's go negative 5 to, I'll try 30. Now, I don't know if that's a good window or not. Well, we'll go ahead and try. Not. I'm getting a not. Are you guys getting a not? So we want to do for our window.
I thought we do 70.
70? Brandon says 70. Let's go for 70. Here we come, and ooh, look at that. If you were to draw a tangent line with our ruler, back from our first activity, right, in Unit 3, if we were to draw a tangent line using that blue function definition, and then draw a tangent line, all right, again, using the red equation, would it appear as though the slopes of those tangent lines would equal one another? Yes, and we forced it to be so. And so it appears as though my function is differentiable at x equals 6. And informally, we can see that the left-hand slope looks like it levels, right? It has the same value. The slope of the tangent line is the same as that slope of that red line, that red piece. So I'm going to go ahead and keep my window screenshot here. I think that was a good window, Brandon. So we're good to go like that. All right. So then, this is not PDFable. We said that was 12x minus 36. Thank you. Awesome. What questions do you guys have about our differentiability and continuity? Okay, so now we're going to go ahead and take a look at our closure together. And as promised, you are going to have a chunk of time to work on your OTL. That's awesome. I knew we'd have a little bit of time today, so that's great. Let's go ahead and decide whether this is true or false. Don't call out. Let's go ahead and decide if it's true or false. You can write true or false next to it. Everybody on your note sheet for today, day 4, I'm looking for a response from each of you. If a function is continuous at x equals c, then it must be differentiable at x equals c. Is that a true or a false? If our function is differentiable at x equals c, then it must be continuous at x equals c. Is that a true or false? Hang on, Brandon, just write it down. We don't want to steal other people's puzzles. We have everybody thinking about it. And then, what 2 requirements do we have for a function then to be differentiable? Okay, go ahead and share your response with the class when I call on you. Let's take a look at number 1. If a function is continuous at x equals c, then it must be differentiable at x equals c. So what do you have for that? Evie?
False.
False? Raise your hand if you have false for number 1. False for number 1? You are correct. Number 2, if a function is differentiable at x equals c, then it must be continuous at x equals c. So what do you have for that? Jake? True. True? Raise your hand if you had true for the second one. True for the second one? Yes, that's right. This will be a quick and easy way to prove continuity. So if we can show that a derivative value exists for a function at a point, then it has to be continuous, and so that'll be the quickest way to apply to prove continuity. What must we show to verify differentiability of a function at x equals c? Well, there's 2 requirements. So what do we have for that? Kobe?
Continuous.
Good. So we have to have continuity as our first requirement. Otherwise, we wouldn't know where to attach the tangent line, right? Where would we attach the tangent line? So we need continuity. And the second requirement, Kobe?
The slope has to be equal from the left side and the right side.
Absolutely. The left-hand slope value or derivative value has to equal the right-hand slope value or derivative value. I'm just going to write that with calculus notation. That would look like the limit of f prime of x as x approaches c from the left must exist and be equal to the limit of f of x as x approaches c from the right. There's our left-hand slope value, f prime of x, thank you. There's our left-hand slope, right? It has to equal our right-hand slope. Awesome. What question do you guys have about our closure? So a function fails to be differentiable at x equals c if any of the following occur. So a function is not differentiable at x equals c if any of the following occur. If we have a discontinuity, then we don't know where to attach the tangent line. So recall our 3 types of discontinuities. What was one type of discontinuity? We're going to just do arbitrarily at x equals c. So what was one type of discontinuity that we had? Riley?
Removable discontinuity.
A removable discontinuity. A removable discontinuity is called removable because we could fix the problem if we were simply to redefine the function at x equals c so it plugged the hole. So a removable discontinuity, right? What's a different kind of discontinuity? Savannah?
Step discontinuity.
A step discontinuity where the function exists at x equals c, right? Or it might not exist, but the left-hand limit does not match the right-hand limit. And so I'll do something like this. We had a step discontinuity. And then what was our final type of discontinuity? Our final type of discontinuity? Sophia?
Like having an asymptote.
Yeah, an infinite discontinuity is a vertical asymptote. Nice job. So if we had a vertical asymptote at x equals c, an infinite discontinuity. Good job. F is not differentiable if we have a cusp, corner, or kink. For a cusp, corner, or kink, we have the function overall limit exists. The left-hand limit of the function matches the right-hand limit, but the left-hand limit of the derivative does not match the right-hand value of the derivative. That is, the left-hand slope doesn't match the right-hand slope. And so we've got a corner, oops, I'll make it the color. A cusp occurs when the left-hand slope does not match the right-hand slope. And lastly, the left-hand slope values could be approaching the right-hand slope values and still not be differentiable in the special case that we've got a vertical tangent. And so we saw that with like our cube root function, where we were approaching a vertical tangent there. It's smooth, the function's nice and smooth, we could trace our pen or pencil tip along the function forever from left to right. There's no continuity issues, and yet it's not differentiable because we've got a vertical tangent at x equals c, and that's not okay. Awesome. Great work today, you guys. You can go ahead and now use this time to get going on your OTL. So we'll go ahead and get going with your OTL today. And you may work with a classmate if you so choose, okay? It's just that I do need the desk back for the cleaning formation for my advanced algebra class next hour, and they'll be taking a quiz. So you're welcome to switch together in partner grades if you want. You're welcome to work individually, however you see fit. Thanks for using this AP Calculus time for AP Calculus. I appreciate that. I'll go ahead and stop the recording now and post it.